Oh, I know what you're talking about.
Then my camera's not working, but we have the screen, so that's okay. You just won't see a mini-me if you go back and rewatch these lectures. Cool. So we had Professor Mundiwala here on Wednesday, and now we're back. The plan was have homework 3 finished by today, but it seems like we are like most of the way there. So maybe one more class so we can talk through like the last, I think 2 problems, right? Or no? 330, 34, and 37. So we have like 3 more problems, but we're most of the way there.
Oh, 2, 3, my bad.
Yeah, and then 37. All right, cool. So we're almost there, but I'll push off homework till like next Tuesday, so we have Friday and Monday to talk through the last few problems. Rectangular. All right, so now we're out on the moon. Copy. Paste. There we go. All right, we're up on the moon and we're driving a rover up and over a hill. And it's so semicircular means like it's constant radius of curvature kind of hill. Which, I mean, roughly that would look like Horsebarn Hill. Horsebarn Hill looks like constant radius of curvature. So imagine you're driving a lunar rover over Horsebarn Hill. Gravity is like 1/10 of what Earth gravity is. We want to know max speed that we can go over the hill so that we don't actually like Fast and Furious off the moon to like, I don't know, smash a satellite or something. Trying to like keep it slow and steady, not Fast and Furious. So, first off, how do you get started? What's your first thought here? Free body diagram? Yeah. Okay. Yeah, that's a good thought. Can we do we need like a full rover like do we need to consider the entire like rigid body kind of structure of the rover? No? What do you think?
I mean, you could do a point mass because you'd be pretty close. I mean, technically, there are like 2 sets of wheels, so one set of wheels could be on the ground, the other not. But
yeah, so maybe there's a wheelie sort of thing, but
yeah, we're approximating. Yeah.
But we can approximate at least for like for the question that we're trying to answer of like, will we lose contact with the ground? Not how will you lose contact with the ground? Like, is the front wheel coming up or the rear wheel? We can kind of approximate it as just like 1 point. I don't care about moments of inertia. Cool. Some lunar creatures and stuff, yeah. The important details. So what is free body diagram?
What did you say? It's a drawing. I'm not a It's okay, you're engineering me, you don't have to. We got normal force. We actually need the normal force. Yes. You know what? I've had a realization. If the normal force is 0, we're no longer in contact with the ground. Yeah. I think I might be onto something, or I'm onto nothing. And the normal force, the normal force is dependent on gravity. No, it's not. Look, I'm like 30% of the way there.
Normal force is dependent on how much you push into the object. So like
As
a
a result
wall.
of gravity.
A wall.
Okay, for this force.
Yes, for this one.
So we actually need to track the normal force. Bless you. Be blessed.
So this is like this.
Yeah, but
Yeah, normal
at
force
a
is
constant
It's straight up.
well, no, it's not a constant direction because it's like
we do not. Actually, I think you're both right. It depends on the gravity strength. What? It's going straight down. The normal force? The normal force.
The normal force always points toward the center of the moon.
What are you talking about? Normal force is perpendicular to
Normal
the
force is perpendicular, but gravity.
Gravity
Always points towards the center.
Yeah, because when you're shifting, gravity pushes you straight down.
They're always anti-parallel at any point. You know what I'm saying? You know what I'm saying? It's always anti-parallel. Actually, is that how true is that though? Because like, if you're just going over a small hill, gravity isn't changing enough.
I think it's just straight
to be relevant.
It would just be.
Oh, because it's on a hill, not.
It's not like on the moon.
I thought that was the radius of the earth.
No, if it was, you'd be right.
No, this is like.
So during the whole time, gravity is always down the whole time. If you're going around the whole moon, gravity would always be anti-parallel to normal.
Yes.
Why are we making this hard for that?
Look, there's a little red creature on the.
Yeah. So I saw gravity kind of pointing down. Seems good. What about that normal force? Where's that one pointing?
I mean, it depends on where it is on the hill, but it's always going to be perpendicular to the surface.
Okay.
Perpendicular, like tangent line, like where it's at on the hill.
Yeah. Okay. So at least kind of roughly, like if I'm drawing it on this one, it'd be something like not, if it's at the top of the hill, then yeah, it's directly anti-gravity. Like gravity points down, normal up, but in general, it's always normal to the surface. Yeah, it's normal as in normal for like 90 degree, not normal as in like, oh, it's totally normal. Like it's always there. All right, now. Oh, sorry, were there other forces? Those were the two that I saw.
I do like friction just because.
You want to put friction in?
Yeah.
Which way?
Maybe against the motion.
Against motion?
Yeah.
What do you think?
Also perpendicular to normal force.
Perpendicular to normal?
It'd be a very smooth hill.
Pretty sure the moon, the moon dust is like low friction.
We'll just say we have extra talking.
What is the external force driving the lunar car forward?
It is friction.
But it's going at a constant speed, so we don't care.
Yeah, but so it's not to say that there is no resistance to motion, but we separated in, so friction, if you're using rolling to like drive yourself forward, friction is your external forward force. Like that, the dominating force is like static friction, that the wheel's not slipping, therefore you move forward. But there is rolling resistance, like a sandy moon with these like big soft tires. Maybe that we can say like there's also some kind of like force of friction, like static, but also like a rolling resistance. Rolling resistance looks exactly like friction. It's just that now you have a mu rolling resistance, like a different coefficient. But it's good to know like what table to look up, because if you're, as an engineer, like our life is governed by tables, right? Like tons of tables to look things up. So when we know something's rolling resistance table lookup is the thing to do. Yeah. Cool.
There's friction going to the right, and the right one going to the left.
Wait, what's the
RR, rolling resistance.
And the other one is on that.
Oh, the friction.
I just wrote friction.
Frick. Wait, it says F subscript what?
S.
Oh, it's just.
Like static friction.
Oh,
Yeah.
Using the air hypertension words.
Yeah. Or it could be like you could think of it as a driving force, because the more torque you put into the motor, the bigger the force that static friction is. So the more forward force you have. All right, acceleration. What does our acceleration look like? It's 0?
No, it's changing as it's on the hill.
I mean, yeah, but like.
Constant speed. 0 acceleration.
We have the direction is changing.
But direction changes.
We're technically accelerating.
Well, we're
Accelerating.
trying to get to fly.
1.6 meters per second squared down.
I think. Not moving? Yeah. Yeah, we could say theta dot is constant or speed is constant, because they should be the same. What is acceleration? Yeah, it's just pointing. Okay. Yeah. So how do you draw? So draw down. Where does it arrow point?
It's just
Okay. Oh, tangent. Tangent acceleration.
Are you sure? That doesn't sound right.
The kinetic diagram is for motion.
Okay, it's moving.
What do you think?
Moving forward, I don't know.
Yes,
Yes,
that's
like this. Boom.
Yes.
So I said it was.
Okay. So you think there's an A tangent to?
Yeah.
Okay.
I have to go with velocity. Yes.
No, the arch would be there.
Off the ground?
You should check out the Pearson. They have one.
Oh, yeah.
I know people probably say that, but it's say it, but they're actually.
No, they've been on.
Low key. I actually have to get off to the house.
Yeah, I don't have it. Oh, wait, no, that's nice.
No, I didn't. No, I had another.
Oh, okay. Yeah.
No, yes. No, I want to make sure it wasn't.
Okay.
Not a great circle. So far I've heard like a few suggestions that like acceleration's going to always be tangent to the circle.
This is kind of like.
You think so?
But it goes all the way around. But it's not like accelerating to the left or right. That's the problem, right? Because that'll be zero because we're moving at constant speed. So
Okay.
my understanding of kinetic diagram is like not super strong. Like, are we trying to get velocity or acceleration?
Kinetic diagram is always describing acceleration. So
Yeah, but get rid of that. Get rid of it.
So in this case, like if we were talking about like what does momentum look like, like yeah, momentum has to be along that curve. So this would be like integral of our kinetic diagram. But if your momentum is always like tangent to the curve, constant, if you're like swinging something around in a circle, which way is the chord? Which way is the force of the thing?
It's always
Like
inwards.
Inwards?
That's kind of like this. Like there's no MA. There's MV to the right. So there's no MA to the right because we're moving at constant speed. So there should only be an aerodynamics. And the reason you know, I guess, is because your MV is so you take the derivative, it's 0.
So like MA this way, more like that? Because really what we're doing is like taking a constant magnitude of MV and trying to twist it around in a circle. So somehow we need like 90 degrees to that, just keep changing the direction. We don't want to increase its magnitude or decrease its magnitude. We always want it perpendicular, constant speed. Kind of like that.
So the top diagram is not the kinetic diagram. It's actually our the integral of it.
Yeah.
Because so kinetic diagram is acceleration. So if you take the integral, you get velocity.
Yeah. And that one, we'll take another look at that. This is called like a momentum. Like if you want to look at momentum diagrams, momentum is directly related to integrals of force. So if you integrate a force over time, then you end up with momentum. So same thing with integrate MA, you end up with MV. Cool. Yeah. All right, what kind of, so MA, we know it's kind of like pointing towards the center of the hill, right? So if this is all, if I draw the hill, it's like, so I've got N, so MA kind of looks like that. And then N plus MG, those vectors equal MA. What is A here? What do we want to say? What kind of coordinate system do we want to use?
We just assume that it's at the top of the hill.
Polar.
We can use the Cartesian coordinates since we know that everything is like within the same axis.
Okay.
The angles we have to deal with.
Yeah.
Yes.
Would you rather know all the points?
So if we assume theta is 0 or small, something like that. Small angle. We could do small angle.
He thinks the angles are small.
Something like that. What do you want to do? Polar could work. Okay.
You have the radius be like constant. It's like
Radius is constant. Yep.
you just change theta.
Projecting in 3 dimensions. Almost how we took calculation.
And then, yep.
Would you mind just dropping the wisdom on where you got those again? Those are just from this book.
These, again, like it, you can always derive it. So if you're on a desert island and you're like, oh my God, I need polar coordinates, you can always start from the definition of what is position in a polar coordinate system, then take derivatives. but normally we're not on desert islands. There's table lookup. So in the book, we can say like, all right, what is acceleration when I have polar coordinates? In most physics textbooks, like at the end of the chapter, it'll have, hey, look, you're in a polar reference frame. This is velocity, that's acceleration. And I dropped the terms. I knew R was not changing, so I dropped it. Theta dot is constant, so I can leave that one. But then theta double dot, constant speed, means theta dot is constant. So that one becomes 0. R dot, I knew that was 0, so that one drops out. So it's nice when all that stuff is just like, whew, gone. Has anyone seen this inertial frame? Well, you've probably seen it, but you might not have called it an inertial frame of reference. Do you know what this one is? It's this next one. Yeah, like v squared over r. What's v squared over r? What was that term? Do you remember that one from like physics? Centripetal acceleration? Yeah. So that one is like, if you only have centripetal acceleration like we have in this problem, then it's a special form of this system where you can say, I know what path I'm traveling on, so the change in speed along that path is all like s double dot, like dv dt, and then v squared over r is describing how the path is changing. So we've got two options, right? Oh wait, that one's, what do we call this one? A T. Oh my God. Oh, I'm blocking it. So we have two options to describe A. So if we take sum of the forces equals ma, what does that look like? Whether you want to use polar or inertial frame, you can pick your poison, but either way we'll still end up with the same equation. It'll just look like a little bit different because we're starting with different assumptions, different kind of like views of the same problem. I guess the other option was Cartesian, just leave it as Cartesian, but no? Okay. You don't want to look at theta dot?
You just multiply.
Okay, yeah. Well, here, like, r times theta dot is v.
Oh.
So it's, yeah, you end up with v squared over r, no matter what.
Okay.
Yeah.
That looks nice.
Yeah, yeah.
What are we doing?
And the optional quiz?
Yeah.
Did you also get a 5 out of 6 on both quiz?
I started it, and then I forgot about it.
Dude, I got the same multiple choice question around for you. Great. So the picture. Where's the shear center?
Because the shear center is the imaginary ID.
That's 0, so just
I put in the thing and then on the right. It was a shear plane. So I guess here, and then I guess here. I think it was here. Why is it here?
We did that little conversation with the imaginary ID. Like where it's
Okay.
I don't remember that. Yeah. I know, it's really annoying, but you know. I don't know why.
No, I mean either way you can have
Yeah.
And the thing is, even if you get like even if you get
We have options.
No, well, what are we supposed to do down?
find MA. I'm pretty sure it's literally just M times AR.
is B squared over R. No.
Because do you not also
Easy to
add
solve the theta dot. It's this.
MG? Oh no, MG. So MG.
So it would just be, yes, that's just the.
Are we doing it in like
Right,
polar reference frame?
Yeah, I'm trying to I don't know whether show me negative.
Okay.
Why is this guy zero? What's theta double dot percent?
A theta dot, no, A is theta is what you're changing to, like, so,
Oh, so that's what it is.
so zero because there's such a constant velocity of
Yeah, so it would be.
Yeah, you're saying you're constrained.
Yeah, I turn some of those off.
Actually, over here we want to oh, I guess
Yeah.
Oh, wait.
No.
At least based on how we since we set it up.
Yeah.
I haven't found the link that they use. Like when I was a senior in high school, they made us all sign up for it and like make a resume. But I didn't put my resume on LinkedIn, so I couldn't get out of that.
Did you guys have to take personal finance?
No.
No, it's a Connecticut.
My school's in Connecticut.
I think it's a new thing.
It might be a
Yeah, it was a new thing before, it was a grade above.
I think it's all for.
And I haven't taken it, and my teacher got grade themselves. She wasn't, she wasn't,
It's always
she was every.
I had 3 different English teachers in the 7th grade. No, they just hated the school. One of them quit in the middle. They just had enough of it.
That's basically.
They were like 3 years. First one was good, the second one, she did, yeah, and then she got fired because she was giving out she did this first one she was doing because she wasn't like reframing, she just really like was personal, really like talking to people and helping people, but she crossed like a student teacher professional. Yeah. So it wasn't like she did anything. It was trying to like write as much as they had to put it on the book, but it was not. Yes, it was not.
Like you learn more by guessing wrong.
Otherwise,
By watching.
But yeah.
So you're right, that's yeah.
But it was like that.
I don't understand if we're supposed to add the acceleration.
Add acceleration
Like,
and
we
subtract.
have sum of
Yeah.
forces equals MA, so MA equals, like, just N plus MG.
Well, we know what is not zero.
All right.
Looking for strictly like the radial forces, so like N and G, but like the
Yeah.
radial component.
So, like, as we're kind of looking at this, anytime you have vectors, it's always 2 equations, right? Like there's gotta be 2 components. It doesn't have, it can be X and Y, like left, right, up, down. It doesn't have to be. We can choose any 90-degree set of components. So in this case, like circular problem, it kind of makes sense to use a circular coordinate system. You can work your way, like if you choose Cartesian coordinates, you can always get there, but it's square peg, round hole. You just need a lot of math, a big math hammer to like jam your way through it. It'll work eventually. But if you're doing it out by hand, it usually saves you some work. So what we're trying to do is figure out like what's happening along that line. Let's use some different colors. Like what happens along that line versus what happens along that line. So our radial stuff versus our transverse stuff, something like that. So what forces are acting like up along that first normal force? And that one, there's no like component of normal force because it's just normal to our path, right? So normal is just a positive n. What else is acting along, like up along that way? Some mg component, right? How much of mg is? That cosine. Yeah, we'll use some parallelogram stuff. So the theta's over here, so theta's over there. Right? That's some wacky geometry proofs. Two parallel lines with a line intersecting I forget what that one's called. Interior angle proof or something? Or maybe it has a name. Like, I don't know, a Greek. Positive or negative? Is it going up or is it coming towards the center? Down, right? And those were the only forces acting along that line. So even if I do add like my driving force, static, my rolling resistance backwards, all that stuff is happening along the path. So it's all going to add up to 0 because we're saying that V is constant. So that's our only two forces. All of that is equal to that one. So the other component is 90 degrees to it, so it's not going to be part of this equation, at least for that like radial kind of outward thing. All right, and now so these two forces, at least these components of these forces, all equal MA. Is that?
Which is called MA in the radial direction.
Yeah, but MA is pointing along that radial direction. So what is MA equal to? What are we using?
So we read MAR, and we know AR is that minus R theta dot.
Okay.
Wait, can you say
Because we took all the forces in the radial direction, it'll be MA in the radial direction.
Like that?
AR, and we know MAR, yeah.
Like negative MR theta dot squared? Or MAR, or M times AR, and AR happens to only have a negative R theta dot squared. So we're done? We solved it? So now, yeah, because really what we're asked for is like how fast do we need to go so that we don't lose contact, but we have two unknowns, theta dot or V, so V and theta dot are connected, and N.
we can assign that. Because N needs to be a positive value if it's in contact with it.
Yeah.
So set N to 0. We'll find
Yep.
max speed.
Because normal force, you can't have a negative normal force. Like you can't stand on the ground and have it pull you to the, without like magnet boots. Or, what were the boots called in Rick and Morty that they can just walk on anything? I don't remember. It was like first episode anyway. But anyway, those boots, they always have like positive, negative, normal force on them. We don't have those. We just have regular tires, normal NASA tires. So if we're looking for speed, speed is R theta dot.
We have R theta dot squared.
So R theta dot squared is V squared over R.
Why do we want speed?
Well, we're looking for how fast we need to go over the hill.
Yes.
So we can report it in terms of theta dot, but then it'll change, like, it'll just be kind of weird. It's like, well, what is 0.03 radians per second in terms of my speedometer? Because we're trying to figure out. At least I don't know how to drive at 0.03 radians per second. I can drive at 20 miles an hour, but I can't do trig in my head at 20 miles an hour. So I could replace all this and say v squared over r, and then we're just back to inertial frame anyway, but however we want to do it. All right, so we have an equation. What is our V max? What's max speed that we can go? Or if it's fast and furious, min speed, because we want to go at least that fast so that we lose contact with the moon, we can hit the satellite, explode the virus, and save the day a quarter mile at a time. What does that V max look like? Okay. Yep. Use like okay. Yeah, that works. Yeah, that's good. And then like 12.
No, because there's parties.
That ends up being
I think there's.
No.
Okay.
Why is that? Oh no, it's being multiplied over.
Because n is 0, assuming n is 0, so there's negative.
I know n is
do
0.
that.
Yeah, do we just say?
That means there's n.
I was saying, I said that 40 minutes ago.
No.
I've been ahead of this. I knew.
Yeah, that it has that. Yeah.
Okay.
So it's about
You can do equal, yeah. Or you can say that it's less than. Yeah. We're leaving that cosine for do you think it's a function of where it is on the hill?
So I got r m squared g cosine. But it's the square root. Did you get that as well, Mike?
Okay.
M squared is equal to
Yeah, and then meters change.
Yeah.
You think you have no weight?
I don't know if it's 20 miles per hour. And I gauge the stagger.
Oh, okay.
Do you think would like the scale times 3 dimensional analysis?
I mean,
Kilograms per pound, millimoles.
Yeah.
I do not. I wonder if they know about feedback. Oh my gosh, we're almost at 100 subscribers. We need to step in this. If you're watching this and you're not subscribed, please subscribe.
Okay.
Well, Mike, do you know about the beam battles Discord? Well, they have a channel called the Gym, and everyone just posts gym on it.
The most sane Discord server. That's why I don't use the gym anymore.
It is all game.
Yeah, can I import a custom beans?
Well, you get like a free, you get like 2 or 3 free loot boxes at the very beginning. I know that. I got like a free black bee.
So I'll show you at least the way that I would think of this. I know if I can calculate n in terms of everything else, I know that n has to be less than or equal to 0. And I know that n is mg cosine minus mv squared. So mg cosine minus mv squared is less than or equal to 0. At least if you're looking to like formally say, how do I get the range of v. Like, so if you just set it equal to 0, then you just have like, okay, go over this hill at 1 speed. But really, there's a whole range of speeds that you could go, right? Like if you're doing 1 mile an hour, you're totally fine. If you're doing 52 miles an hour, now you've gone over the limit. So the m's cancel out. It doesn't matter how big the thing is. Something like this. What do I do with that cosine theta? What am I supposed to do there?
Well, it's a very small.
Very small angle? Yeah. I like small angles.
I love small angles.
Small angles are
I'm pretty
great.
sure the cosine is really small angle.
Small angle? Yeah.
Did you just say like cosine at its maximum?
Or we could say like worst case scenario that v squared has to be more than or equal to the 1, like the max component.
Isn't cosine theta where theta's tiny, just 1?
Yes.
So let's say we do say the angle is, let's do the opposite. Let's assume that the angle can be large. What does the hill look like for a large theta? Like if theta is 90 degrees, how steep is the hill?
That's a vertical.
A vertical hill, because now you're talking about like a dome. You'd be climbing like the side of Gamble Pavilion, right? Because that's a dome. And Gamble is like very large radius, but a hill is just sort of like just the top of Gamble. Like if you're walking around on the very top of Gamble, no problem. If you're trying to climb the sides, now you're like actually scaling a vertical wall. And that's not even the full dome. So the smaller that section is, so if you take like that full circle, not a great circle, and we're just saying like, just cut it here. And that's my theta. So theta, it's a pretty reasonable assumption to say theta is pretty small. So therefore, this is going to be about 0. So now I can say RG less than or equal to v squared. Cool. So what's v? How fast can we go? I think I saw like numbers 16. What else did people get with?
I think the range is 1.6. Then the square root of that. I got 17.
Radius is 1.0. No, what are the numbers from the problem?
And I feel like, did I mess up?
Oh, I used mass instead of radius. I'm silly.
I feel like v has to be less than rg. Is that right?
I got 12.
Did I mix something up?
Wait, what? Why would I have to feel?
Or wait, more than? Because that would mean we have a lower limit, right? Less than? More than? What do we think?
12 points?
No, we need an upper limit, otherwise if you go too fast,
Yeah, yeah.
you'll fly off.
So shouldn't it be less than equal to?
Yes.
So I think when I brought that v squared over r to the other side, I had to flip it.
No.
No?
You brought that n to the other side.
Isn't that just addition and subtraction? I don't think you divide anything.
Yeah, I didn't divide anything though. But isn't it saying v squared more than? What did I do wrong?
No, it's v. Wait.
Ours is not big enough.
Are we good?
Come on, let's go back to the beginning. Let's just start.
Yeah, yeah.
The beginning's usually a good place to start.
So positive n, negative mg. So mg cosine minus mv squared is n. N is less than. Oh, n has got to be more than 0, right? Yeah. That was it. I'm like, why am I missing? All right.
Oh yeah, because then we can't have negative n.
We can't have a negative n. That was the problem. We were solving for all the cases when you fly off the moon.
Which actually that is still the speed limit.
We solved for something. So less than or equal to, what was it? 12? So we'll call it 12.7. And that's meters. Yeah, still like 25, usually like multiply-ish by 2, 25 miles an hour. We're moving.
Multiply meters by seconds. Meters per second by 2 approximate miles per hour.
Roughly, yeah. I mean, it's not exact. Yeah, 12 is 26. So 2 point something, right? All right, there we go. Yeah, make sure n is more than 0, not less than 0. There we go. All right, cool. Oh, we have 5 minutes? That's not enough time. Fun fact?
Oh wait, Professor, before I forget.
Yeah.
All the people in this class who are also in mechanics and materials are going to have to leave early on this because there's an exam.
You have another exam Monday?
The professor likes to start them early, so we're going to leave early. But
Yeah.
it's not because we don't like you, it's because...
It's okay. Yeah.
Okay. Just want to give you a heads up.
Thanks. Yeah.
So you just like wonder why 5 people just like check out the same.
Yeah. Good luck on the exam. What's coming up in mechanics and materials?
That's a good question.
What is it about?
Are you sure you're not going to cook again? Just make shit up like you're going to
Because that one's all, it's all the same like stuff that we're doing here, like kinematics, and the only extra step is that now you also say stress is modulus times strain.
It's a lot of stress right now.
You're doing beam.
Beams has been well over.
Are you doing plate theory?
Not yet.
Okay, all beams. Yeah. All statically
Tables for the different kinds of beams.
statically determinate beams or indeterminate beams. So you need to know like how much it bent to figure out how much moment there is.
I think that a little bit.
No?
Shear equations. No. You know, like moment of inertia.
How much force do I need to put into drywall before I make a hole?
Yeah, because you have like W of X. W is a function of length along the beam. So like moment is EI second derivative. And then shear force, that one I forget, but yeah. But second derivative is always, curvature is always moment. Yeah, that one's good to know. All right, cool. Next time, I think we just have 2 more problems, right? Double check. 2 more problems, so we'll space that out. Today, I think we deep dove into 1 problem. We'll like fly through next 2. That'll be the plan. All right, cool. Thanks so. Oh yeah. Yeah, we'll push it back to Tuesday. Yeah. Yeah, and I'll do that now. Hey.
No, I think like you just
touch on that next semester if you have time.
Yeah.
So I'm a dual minor, so I don't have a lot of time in my schedule, unfortunately. But I wanted to take your section of computational mechanics, but it filled up. I know I have
it filled up fast, right? Yeah.
Almost immediately, within 2 days.
Yeah.
I heard that I have to fill out a form, but I wanted to talk to you first because I know some professors don't like going over. So wanted to check with you.
Yeah, that one, you can fill out that form. Usually it has to do with like how big the classroom is. And yeah. So yeah, but the other thing that I offer is like over the summer, I teach a 5-week comp mech, and then over the winter, I do a 3-week comp mech course.
I'm very excited for computational mechanics. I'm also doing FEA for BME next
Oh,
semester.
you are? Oh,
so
cool.
I'm very
Yeah.
excited for both.
Nice. Who teaches the FEA course?
I think it's Bin Feng.
Okay, nice.
Yes.
Yeah.
Very. I've been hearing about that for like 2 years now, and I've been really excited to start it.
Oh, cool.
Yeah.
Yeah.
The FEA one though only has 10 seats, and it's one section.
That's cool. That'll fill up quick too. Yeah.
Oh, I already got it.
Okay.
Yeah,
All right.
I
Yeah.
went
Yeah.
big time yesterday.
Nice. Okay.
Thank you.
Okay. Yeah. Hey, how's it going?
It's going pretty good. I finished the wind portion of the project where I took an example of a wind farm in California.
Yeah.
And went through the equations we talked about, and
Still, I thought. Sorry.
I got like a number that